All right, guys. So this is lecture 6, and we're going to be doing integrals with logarithms and rational expressions. And so let's see here. Basically, there are a couple things going on in this homework set and section. So what we want to do is learn how to do two different types of integrals. So we'll learn these types. Basically, how to do an integral of a logarithm like this, log base ax. And also, we're going to learn how to do integrals of this sort. Okay, and those are both related to logarithms. And when we say rational expressions here, we're saying that because if you have certain types of rational expressions where the bottom is the derivative of the top, then it'll be this type of integral. You'll just have to do a u substitution first. Okay, now in order to do this, here's how we will get started. So we'll start with this type, just the type with logarithms. Okay, now there's a technique for integrating a logarithm like this called integration by parts, and that's usually how this topic is taught, but in our book we're learning it out of order basically. So it will be presented in a slightly different way here than I would normally do it. So consider this derivative. So consider this derivative. Consider the derivative of ln x minus x. Now the thing here is y ln x minus x. Magic, that's why. Okay, so there's no reason to know why we should be looking at this. It's just what we're looking at. Okay, so we're looking at this derivative. So let's take the derivative. So if you were going to take this derivative, actually, let me back that up. If you were going to take this derivative, x ln x minus x, then the way you would do it is you would need a product rule for this part, and the x is going to be easy. All right, so let's take the derivative, and we're going to use the product rule. So to take the derivative of x ln x with the product rule, it's going to be x prime ln x plus x ln x prime, and then when we take the derivative of that x there, it's just going to be minus 1. Okay, so there's my derivative. Now the derivative of x is 1, so you have 1 ln x plus x. The derivative of ln x, is 1 over x minus 1. So we have ln x plus 1 minus 1, which is just ln x. All right, so what we discovered was the derivative of x ln x minus x is ln x. All right, now why do we want that? The reason we want that is because every derivative formula is also an integral formula. Every derivative formula is also an antiderivative or integral formula. So we can take that expression that we just came up with here, and we can rewrite it this way. So the antiderivative of ln x dx must be x ln x minus x plus c. Sure, why not? Oval. There you go. And so that's a formula for taking the antiderivative of a log. Now, most of the logs that you're going to see are probably not going to be natural logs. So then the question is, how does this formula change? And so the way it changes is if you have an integral of a log base a of x dx, it's going to be basically the exact same formula, x ln x minus 1. So like x ln x, minus x. But then there's an extra 1 over ln a. Okay? And that's going to be the only difference. Now, I think that the way your book likes to write it is actually like this, so I'll rewrite it. Your book likes to say x over ln a ln x minus 1 plus c. Okay? Maybe I will delete this and try to put a box around it. Hey, okay. So those are the formulas you need in order to do this first type of integral here. Okay, so what's your homework going to look like after you know those formulas? Well, it's going to be pretty easy actually, right? You're going to have example integral 13 log base 15 of x dx. Well, I mean, all you're going to do is you're just going to recognize that this is 13 integral log base 15x dx, and then you're going to use your formula. And so your formula, right, we got your formula says we're going to need basically just to know what the a is, and then other than that it's x ln x minus x, or the way that they wrote it, which is slightly different. So we just do x over ln 15 times, well, just parentheses, ln x minus 1 plus c. And, that's it. That's all we have to do. So, problem solved. Probably need to see more than just one. So let's do that. Well, maybe one more. I feel like they ought to do some definite integrals in here. And I don't know if they do. But let's try another one. Let's do a definite integral, even if they do not. Let's say we're going to go from 1 to 25 of 3 log base 5x dx. That should be fine. Okay, so this is a definite integral, so that means we're going to be doing the fundamental theorem, which means we need the antiderivative, and then this needs to be evaluated between 1 and 25. So the 3 is just a 3. We can take that out of the integral, so I'll put it there. And then we need the antiderivative of log base 5x. And again, it's a very easy formula, right? It's right here. X over ln a, so that's x over ln 5, and then ln x minus 1. Like that. Okay? Now, after that, you'll plug in your 25 and you'll plug in your 1. So you're just going to have 3 25 over ln 5 ln 25 minus 1. That's what you get when you plug in the 25. And then you need to plug in the 1. So you're going to get 3 1 over ln 5 ln 1 minus 1. And there's probably some simplifying you can do here. I'm not really going to do much. Let's see here, what can we do? I do know that ln 1 is 0, so we'll use that. And so that's 0 minus 1 minus 1 times a minus is going to be a plus. So I think it's just 3 over ln 5. Like that. So, if you want to write this in a nicer way, feel free. I'm just probably going to just stick with that. Okay. So I don't think there's a lot to say about these. Again, the point is that we came up with these formulas just by working backwards from a derivative. And there was no explanation for why we should be looking at x ln x minus x in the first place, but we did, and it turned out to work out. Okay, so you do a few of those integrals, and that's all you're going to be doing for that part of the homework. However, we've got another piece of the homework, right? And the other piece of the homework was that 1 over x type integral. So we know this. So what did I call this section? I didn't. Okay, so let's look at the rational expressions one, which really are not very many rational expressions. It's not all rational expressions, but it's just the 1 over x type. So we know this. Again, we'll start with the derivative. We know that the derivative of ln x is 1 over x. Okay? That means, as an antiderivative formula, the integral of 1 over x dx equals ln x plus c. But there's something missing here, and that is as follows. So this function right here, the 1 over x, you're allowed to plug in positive and negative numbers in there. You can plug in plus or minus numbers in there. You can't plug in 0, but you can plug in positive or negative numbers. But here you can't, because the natural log is not defined for negative numbers. Ln x is not defined for negatives. Okay? So, what's that mean? Well, basically, the reason it happens, first of all, is because if you look at a graph of 1 over x, you have a graph over here on the right, and then you have a graph over here on the left, and they're basically just the same graph, okay? And so integrals are related to areas. And if you have an area over here, like that, and you have kind of the same area over here, like that, they come up the same. And because they come up with the same, if you want to modify this formula here so that it works for positive numbers or negative numbers, it actually has a very simple change to make. So to make it work for positives and negatives, instead of just positive numbers, all you have to do is add an absolute value in the right place. Just do this. And so this is actually the formula that you need to know. So the antiderivative of 1 over x dx is generally not written as ln x, it's written as ln absolute value of x plus c. So that way it will work for positive numbers and negative numbers. Okay, so actually use the formula below. This one. Okay, so that's the formula that you need. And so once you have that, now you have a whole bunch of new derivatives that you could potentially do. Okay, now most of the integrals that you're going to have to do on the homework are going to be like substitution integrals. Okay, so they're going to be not just 1 over x, they're going to be more complicated than that. So like, let's see here, find a good one for you. Yeah. So most of the problems are going to be like this. So most problems you see where this applies will be substitution integrals. Where the top is the derivative of the bottom. Okay, so here's a pretty simple example. So, and then we'll do some real ones. So let's say I have this integral right here, 2x over 1 plus x squared dx. Now that's an integral that you will not have known how to do before now, but we'll be able to do it, because if you take this down here and you let that be your u, let u equal 1 plus x squared. I should use a darker color, that's hard to read. U equals 1, I should erase it too. Let u equal 1 plus x squared. Okay, then your du for substitution is going to be the derivative of this. The derivative of 1 plus x squared is 2x dx. You'll notice that you actually happen to have a 2x dx there. That means that you can rewrite this integral as, well, I'm going to take 2 steps just to make it really obvious here. So you have the integral of 2x dx over 1 plus x squared. That's the integral of, well, the 2x dx, right? This much, well, that's this much. So that is just simply du. Then in the denominator, of course, you have 1 plus x squared, and 1 plus x squared is just u. So this turns into the integral of du over u, which is the same as this, right? The only difference is whether you've written the du off to the side or whether you've written it in the numerator. So this is just the integral of 1 over u du, and we know what that integral is. It is natural log absolute value of u plus c, right? That's what we just learned. And then after you have it, all you have left to do is you've got a u here, and you've got to replace the u with what it actually is in terms of x, and so you get natural log absolute value 1 plus x squared plus c. And that would be your answer to this integral. Okay? So that's the basic method that you're going to be employing. And so the top is the derivative of the bottom, right? That's what you're looking for this to apply. Now the thing is that it's generally not going to be as perfect as this example, okay? So what I mean by that is, well, let's just do a different one. Example. So let's say you have the integral of 50x plus 10x cubed over 10x squared plus x to the fourth, and then dx. Okay, this is the same type of integral. What you should notice right away, like, you don't know for sure when you look at this whether or not it's going to work out with a substitution, but what you definitely want to notice is that, you know, this is a fourth degree and this is a third. So those, like, the term on top could be the derivative of the one on the bottom. And the same thing over here. This is second degree and this is first degree, right? So the bottom is degree 2 and 4, and the top is 1 and 3. So the top looks like it could be the derivative of the bottom, and that's the kind of thing that you want to notice. Top looks like it might be the derivative of the bottom. Now, in order to work it out, you've got to actually take the, try to make the substitution and see if it works. Okay. Just because it's the same, just because the degrees work out, that doesn't mean that it's actually the whole problem's going to work out. So my advice is going to be, on the top, first thing you want to do is factor out that whatever you can. Or, sorry, don't factor out whatever you can. Just factor out the constant. So I see the 50 and I see the 10. And I say, okay, well, let's just take out the 10. That'll be helpful. And then I'll have, what will I have? 5x plus x cubed. Okay, and I'll just put the dx there. That's fine. On the bottom, do nothing. All right. And then you're doing that just because this is going to be a more convenient form to have that. Okay, that and this. That's what we'll be trying to match when we do our substitution now. Now for the substitution, we want to try, we want u to be the denominator, right? Same as we did on the other one. Du is 10x squared plus x to the fourth. So you take your derivative, you're going to get 20x plus 4x cubed, and I should have a dx there. Let me move this over. Move. Why you no move? Okay, there we go. Dx. Okay, so there's your du. All right. Now again, look at the part that I highlighted though. I've got like a 5 right here, right? And here I've got a 20. But you can factor out a 4 here and have 5x plus x cubed dx, and then you can take this 4 and divide it off to the other side and have du over 4 equals 5x plus x cubed dx. And now this right here, this is going to match what we have in our numerator. So once we've done all that, now we can try to make our substitution. So what we'll get is we've got this 10 that we factored out. Then we've got the highlighted part. Looking at this, we see that the highlighted part is just du over 4. And in the denominator, of course, we have this 10x squared plus x to the fourth, but that is what we're calling u. So this is what you get when you make your substitution. So you've got the 10 over 4, which I'll just take on the outside, and then integral du over u. So it did work out, right? Du over u, because we know that the integral of du over u is natural log absolute value of u plus c. And of course, 10 over 4 is going to be, 5 halves. So you have 5 halves ln absolute value u. You don't want to leave your answer that way. You want to substitute in what the u is. And again, looking up here, we see that u is 10x squared plus x to the fourth. And there you go. All right, so that's another example. And that's more typical of the difficulty on this homework assignment, okay? They expect you just to be doing, substitutions that way. All right, now you are gonna have, definite integrals sometimes. So let's try a definite integral version of one of these. Let's try a definite integral. So we're going to do an integral from 1 to 2 of 9t plus 12t cubed. Let's make this bigger. I don't know why this is so small. 9t over 12t cubed over 3t squared plus 2t to the fourth dt. Right? Now, like I said on the previous problem, I would recommend that in your numerator up here, if you can factor out a constant, then factor out the constant. It makes it easier to make the substitution. So I look at 9t plus 12t cubed, and I say, well, they got a 3. Those have a 3 in common. So let's take out a 3 and have 3t plus 4t cubed. And I'll put the dt there. Denominator, you could do the same thing in the denominator, but there is nothing to factor out, so we'll just write it like this. Okay, and then this is still from 1 to 2. Now we haven't done a lot of substitution integrals with limits of integration, and so I'm going to show you something that I always teach in my Calculus 1 classes, but maybe you haven't learned it or maybe you forgot it. But we'll get there in a minute. So what do we need to do now? We need to make our substitution. So we're going to substitute. Substitute. All right. How do we pick the u? Well, remember what we're doing, right? We expect that the denominator there is going to be our u. Okay? So we want u to be 3t squared plus 2t to the 4th. And then our du, well, we just take the derivative. So we're going to have 6t plus 8t cubed dt. And like before, to make the numbers work out, we want to factor out whatever we can here as well. So I see a 6 and an 8, and I can take out a 2 and get 3t plus 4t cubed dt. Divide that 2 over, you get du over 2 equals 3t plus 4t cubed dt. And we should be able to make this substitution now, because we have, we've got this right here, 3t plus 4t cubed, that matches this right here, right? Everything except that 3. So we've got the top, we have the bottom, which is u, and then we have the top, which is du over 2, just with an extra 3 there, right? So I'm going to rewrite this integral here. I'm going to be careful here. I'm going to say t equals 1 to t equals 2. Because those are not the limits for u, they're the limits for t. And let's try to make the substitution. So we have 3 times, and then the highlighted part in yellow is du over 2. And then in the denominator, we have the highlighted part in green, which is just u. So there's my integral. So my integral is just 3/2 integral from t equals 1 to 2 of du over u. Now I'm going to change the limits now. And this is the part that not everybody does, but is absolutely worthwhile. Okay, so we're going to change the limits of integration. And the way we do that is simply by using your substitution up here. Okay, so I'm going to put a little box around here. Can you make a box for me, computer? Yeah. Ooh. Okay. So here's what we want to do. So for that, you want to take the limits and change them from t into u. So the top limit is t equals 2, right? But then you have your substitution. Your substitution here says that u is 3t squared plus 2t to the 4th. So you simply substitute this into your u substitution. So if t is 2, then u is 2 squared plus 2 to the 4. Right? So we're just putting a 2 into the u substitution. So work that out. So what do we get? 2 squared is 4. 4 times 3 is 12. So 12. 2 to the 4 is 16 times 2 is 32. So is it 32 and 12? 32 and 12? Is that 44? I'm going to write 44. I hope that's right. So we get that. Now you have to do the same thing for the bottom limit. So the bottom limit is t equals 1. And then you take that and you plug it into your u substitution. So u is 3 1 squared plus 2 1 to the 4, which is, well, that's just 3 plus 2, which is 5. So what you want to do with those limits is now those go here on your integral. And the reason you do that is because now you can forget all about the t's that you had at the beginning of your problem, and we can just scroll up here and only pay attention to this integral right here. All right, so let's do it. Let's do that integral. So we have 3 halves. We need an antiderivative. So what's the antiderivative of du over u? ln u, right? That's what we're trying to learn. ln absolute value of u. And then we've got from 5 to 44. And those are in terms of u, which means we don't have to go back to the old variable. We can just put these in here. ln 44 minus ln 5. And that's it. That would be the answer that they expect in the book or in the online homework. Okay? So there you go, that's it. So, summary, what are we doing here? Basically, you just need to be able to do definite integrals with both of these types of, both of these types of integrals, right? So we should be able to do an integral of a logarithm. We should be able to do a definite integral of a logarithm. We should be able to do an indefinite integral that results in a logarithm, which is a different thing. And we should be able to do a definite integral that results in a logarithm. If you can do those, you can do the homework. All right, that's it. I will see you in the next video.